So today I'm going to focus on light fields generated by collimated beams. By now you probably have an understanding of what this first little picture is like. You saw pictures like this in your lab yesterday. This is actually an aberrated phase aberration due to scatterers of a focused beam. And the second very colorful plot is actually this triangle here is looking at spherical harmonic expansions. And these are basically how you can represent any function on the surface of a sphere through Fourier decomposition. And so you have variations in theta and in phi, so you have these lobes. And I'm going to focus on a class of expansions called the PN expansions, and that basically tries to represent the radiance, which is a function that can be expressed on the surface of a sphere with just variations in the intensity in theta. So this is loosely related to what we're going to be talking about today. So I'll start with teaching objectives. So today you'll learn about both the standard diffusion and what we call the delta P1 approximation. We'll discuss how these are derived from the radiative transport equation, which is what we introduced on the first day. And I talked a little bit about the RTE, and Jerry discussed how you can use Monte Carlo simulations to solve the RTE rigorously. And so here we're going to focus on approximate solutions and understand their underlying assumptions and limitations. Now, both these approximations reduce this rather difficult to solve integro-differential equation into series of partial or ordinary differential equations. And so when you have partial or ordinary differential equations, to solve them you must enforce boundary conditions. And so we'll talk about the boundary conditions that you need to formulate in order to solve these equations. And usually these boundary conditions have to handle refractive index mismatch at these boundaries. So we'll talk about how these boundary conditions are formulated to solve these governing equations. Then the next thing that we are interested in is solving the light transport for a source of light. So there are various ways you can express sources or generate sources in tissue, and we'll talk about how that's incorporated in these analytic expressions. And we'll talk about optical depths. One thing that was pervasive in the talk yesterday was, depending on how these vascular lesions develop, these abnormal vascular structures can be at different depths in the tissue. And especially when Dr. Nelson said they were trying to treat adult lesions, you had to go deeper and deeper, and it was more difficult to reach them because you have more scattering tissues. And so to understand how the wavelength of light, the optical properties, the size of the beams affect your ability to get light in deep is critical. And so we're going to start looking at how you can express these optical depths mathematically so that when we visualize these light fields that are predicted through these approximations, we can gain some understanding of how refractive index mismatch and optical properties affect these internal fluence rate distributions, how the fluence decays with depth, and how these properties affect your ability to get light in deeply into tissue. We'll talk about the effect of beam diameter, how that might affect your ability to get light in deeply into tissues. And then finally, I'll end with some results on radiative transport in slabs, where you have thin, relatively thin units of tissue. And look not only at the internal fluence rate distributions, but the light that gets reflected, transmitted, and absorbed. And that will provide, I think, a good transition to Rolf's lecture. Okay? Great. Okay, so we start again with our old friend, radiative transport equation. Just to remind you, this is just a balance equation. The radiance, again, is a function in position. So bold R is a position vector. omega, it represents the direction of the photon. So we just need two coordinates to define direction, a polar angle and an azimuthal angle. Okay, so those two define your direction, and then of course you can use time-varying sources, and time-varying sources are used in many applications, and you'll hear about those applications in diagnostics on Friday. So the left-hand side just considers how can light change with time, and how does the light change along the direction of propagation that we're considering omega. And that spatial temporal change can happen in three ways. One, we can lose light at this location that we're considering due to either absorption or scattering. Okay? Absorption, you lose the light because the photon is actually extinguished. In terms of scattering, the photon remains, but it just gets scattered to a different direction, omega prime. So it's lost from direction omega. And then, of course, we can gain light through a scattering event at that location from other directions omega prime. They may interact here based on the local probability of scattering, mu sub s, times the probability that that photon traveling in direction omega prime gets scattered into direction omega. So what we do is that we take the radiance at all other directions omega prime. We evaluate, well, what is the probability that that light will get undergo a scattering transition from direction omega prime to omega, and then we integrate this over all possible angles, and then multiply that with the local probability of scattering. Okay, so this is a gain term. Okay, this is how photons from other directions get transition through a scattering event into the direction omega that we're considering. And of course, you can have sources that inject light at a certain location in the direction you're considering. Okay, and so this is the equation we would like to solve. It's very difficult to solve analytically. Of course, we can solve it using Monte Carlo, but they're also a valid place for analytic approaches. So before I move forward, any questions about this equation? Are people at least fairly comfortable with the concepts behind them? Okay, so we're going to discuss how we can simplify this equation and actually develop some approximate analytic methods to solve it. So here is the radiative transport equation. So the first thing the field did is said, well, you know, L in general is a very rich function. It has rich spatial information and rich angular information. And one needs to simplify the complexity of the spatial and angular representation of the radiance in order to deal with it analytically. And so we approximate these two functions that are in generally six-dimensional objects, this radiance and this phase function. The phase function itself also can be a function of space and direction. And so what was done is to expand these two functions in terms of Legendre polynomials and actually terminate after the first order term. So this is the approximate analytic representation of the radiance. What we say is that first, the easiest way you can represent this is through a term that is equivalent over all angles. And this is called an isotropic term. We call this, you see, phi, which is the fluence rate. So basically it says, well, let's just take a term that is actually uniform in all angles, not only in the plane of the board, but 3D. So this is just a sphere. It says, okay, we're going to say, well, let's first approximate the radiance by a sphere, equal in all directions. Okay. Now, obviously, we have a net flow of photons in a certain direction. So in reality, you have some bias of flow of photons in one direction versus another. And a way you can get that is through the first order term of the Legendre polynomials, which is essentially a cosine term. And we are representing this by the letter J. and you do a dot product with the photon direction vector. So this is a cosine term. J is a scalar, dot the direction vector. This gives you a cosine term. And if you look at how that modifies this radiance representation, if you have the photon moving from left to right, the cosine will add a little bit on the front side and subtract a little bit on the back side. Okay? So if you have photon flow from left to right, you essentially add a little bit onto the right, because at theta equals 0, cosine is 1, and at theta equals either pi over 2 or 3 pi over 2, cosine is 0, and then you start to subtract things off. And so if you now look at the sum of these two, you can see that you get a bias in that radiance representation, right? You see you have more photons moving forward than moving backwards. And of course, depending on the magnitude of this, that bias can be greater or smaller. But this provides a net flow of photons from regions of high fluence rate to regions of low fluence rate. And we do the same thing in terms of the phase function. Phase function, again, is an angular function. It tries to describe what is the probability of transitioning from one direction to another upon scattering event. And we talked a lot about phase functions and how different types of scatterers have different types of phase functions. Rayleigh scatterers having fairly isotropic phase functions, Mie scatterers having tremendously forward-directed scattering. And you can see here, if you're trying to express your phase function in terms of a constant plus a cosine theta, you can see immediately it's probably not going to do a great job for Mie scatterers, where you have a tremendous amount of light directed directly forward and very small amounts of light in all other directions. But nevertheless, you have the same sort of term here. You have an isotropic term, a constant term here, and then you have a single scattering anisotropy term. This is, again, a dot product between omega and omega prime, where omega prime is a scattering angle. And here is where G arrives. G is the first moment of the phase function. It's the average cosine of the scattering angle. And so for larger values of G, you get larger bias. Just like here, if you have larger J value, you get a stronger bias. So what we do is that we take these two expressions for the radiance and the phase function. This has lower subscript E because the person who developed this phase function is Sir Arthur Eddington. So this is often called the Eddington phase function. So what we do is that we take these two expressions and we put them into the radiative transport equation and see how things fall out. And when you do that, you get two equations. And I won't go into tremendous detail, but essentially what you do is you put both of these expressions into here. You get one equation you can get by integrating the resulting equation over all 4 pi solid angles, so you conserve energy. And then you also generate a second equation, and that results in this first equation here. This results from putting these two substitutions in here and integrating over all 4 pi solid angle. And then the second equation comes about by taking the first moment, by looking at the net flow and making sure the net flow is balanced. So you get these two equations, one for the fluence rate, which is phi, and in our field, J is referred to as the flux. If you look historically in the radiative transport literature, it's a little confusing. They refer to phi as the flux and J as the current. So just in case you are interested in looking at the older literature, don't get confused. Sometimes they refer to what we call the fluence as the flux. So you can use this expression for J, substitute that back into here, and get a single equation for the fluence rate. Just want to describe a little bit of notation here, just to remind you, V is the speed of light in the medium. Q naught is the integral of the source term over all 4 pi solid angle. And Q1 is the first moment of the source term. How biased is that source term directionally? Okay? So, and I can give you references if you really are very interested in going through the whole steps to derive these equations. Then by substituting the expression for J into here, you get a single partial differential equation, and which is written here. This entire equation is called the P1 approximation, and if we ignore one of these terms, which I'll talk about in a bit, you arrive at the diffusion approximation. So the form of this equation is actually something that is not too unfamiliar to those of us who do a bit of mathematical analysis. You have what is known as the Laplacian of the fluence rate. And for those of you who have done either potential theory or heat transfer, in heat transfer, for instance, you see the Laplacian of the temperature. It's like a potential, something that pushes spatially. You have gradients driving the flow of heat. In this case, you have the gradients of your local fluence rate driving the spatial distribution of photons. Unlike heat transfer, for instance, you can actually extinguish photons. So you actually have a loss term due to absorption. So that's the second term here. And this gives you a spatial attenuation rate, which we'll talk about later. So this second term is an absorption loss. Then on the right-hand side of the equation, we have a wave-like propagation term. We have a second time derivative. Second time derivatives occur typically in wave propagation, and you saw that in terms of Maxwell's equations in Janika's lecture yesterday. So here you have wave-like propagation. One thing I would just note here is that typically in wave equations, this is linked to the reciprocal of the velocity squared, and you can see that the velocity is actually wrong. So if this were correct velocity, it should be 1 over v squared, but this actually gives you 3 over v squared. So actually, the velocity of propagation of light in this diffusion approximation is off. You have a single time derivative term, which also you see in potential theory and heat transfer. This is the time rate of change. And then you have a source term. Okay? So this is what's known as a Helmholtz equation. You have 2 derivatives in space, 2 derivatives in time, and absorption loss term. The other thing I want to emphasize here is that in this radiative transport equation, you have a full description of the optical properties of the medium. You have mu sub A, the absorption coefficient, mu sub S, the single scattering coefficient, and the phase function, right? Mu T is the sum of mu A and mu S. You have mu S, and you have this phase function. Here, you have mu A. Mu TR is mu A plus mu sub S prime. Okay, so you get not mu sub S, but the mu sub S prime, which we refer to as the isotropic scattering coefficient. It's the product of mu sub S times 1 minus G. So mu sub S by itself disappears in the diffusion approximation and the P1 approximation. Mu TR, again, is mu sub A plus mu sub S prime. And here you have mu sub S prime. So what that means is that for any fixed value of mu A, all pairs of mu sub S and G, which is the first moment of the phase function, that produce identical values of mu sub S prime results in identical solutions, identical predictions. So you've lost detailed directional information about the light field. And that is inevitable because what we did is that we took this beautiful information-rich radiance and we dumbed it down and just expressed it in terms of 2 terms. Okay? And that's what leads to that loss of information. Okay? This approximation tends to be valid when these approximations for the angular description for the radiance and the phase function seem fairly valid, and that tends to be when scattering is dominant. So scattering, the reduced scattering is much larger than mu A, then you lead to the diffusion approximation. You can basically retain all the terms that I've annotated in red below. If you want to relax this a little more and say, okay, I want to get a slightly better solution, you only want to make the approximation that only mu-s is much, much larger than mu-a, then you need to include this wave-like propagation term. For cases where you have just time invariant transport, these first two terms go away, and for steady optical transport problems, the diffusion and the P1 approximation are equivalent. Okay. Okay. Any questions about this? Yes, Michael. Let's wait for the microphone.
So, like, for people without a background in mathematics, or
yes,
this heavy of a background in mathematics,
yes,
it seems like you start with some assumptions, then you like apply differential equations in sort of the way that they were, meant to be according to textbooks. But like, at what point do you go back and validate that these equations are actually representing reality?
Well, we're going to show results in a little bit that actually compare the results, the solutions of these equations to Monte Carlo simulations. And that is one way of comparing how these analytic approximations, how good of a job they do, and in what cases they may break down. So that's the real power of Monte Carlo, because it provides us a gold standard for the solution of the radiative transport equation. And then we can see, okay, in what cases do we get good or good enough solutions from these analytic methods, and when do we have to be really wary about applying these approximations? And hopefully, not only in today's talk, but in the talks on Thursday and Friday, we're going to be really trying to, that's one of the key overall teaching objectives of this course, is to make sure people understand in what cases are you okay in applying these approximations, or at least you're willing to make the trade-off of loss of fidelity in that solution, versus cases where if you apply this approximation, you're really risking it, so to speak. Jerry, do you have any comments? I mean, that's a really good question, I think. Why don't we get the microphone over?
On Monday in the second lecture, I did discuss in some detail how you establish the rigorous connection between the Monte Carlo simulation and the radiative transport equation. So you know that if you obey those rules, that you have an unbiased estimator and an appropriate probability measure on the sample space of all biographies, then you are solving that very equation. So it's important to remember that that is a rigorous connection that sort of addresses your question. And then, as Vosden said, if you make approximations to the RTE, you have the job of understanding the range of their validity vis-a-vis the radiative transport equation. Yeah.
Hi, Vosden. That's just a little observation here. P1 approximation is a better approximation than diffusion. You're adding one term in the description. However, the condition for applying this term seems more relaxed than the diffusion approximation condition, mu-s prime greater than mu-a. Well, if mu-s prime greater than mu-a, then mu-s has to be greater than mu-a, correct? So it's just a comment. I'm just wondering.
That's a very good comment. Let me, right, you're saying that mu-s prime is always smaller than mu-s.
Yes, yes.
Yes, so P1 is a better approximation, so it's a more stringent criterion. It has to be a more stringent criterion if you want to get this additional accuracy. So this is a more stringent criterion. As it should. Oh no, you're saying it's a less stringent criterion.
Yeah.
Okay, so I need to check that. I know.
Mu-s prime is what 0.1 mu-s, right? So
yeah, for g equals 0.9.
You have
yeah,
mu-s
sure.
Than mu-s prime greater than
sure. Okay, let me check that. Thank you. That's a good point. Maybe there's something awry in what I've written. I'm sure there is. Okay, but thanks. Yeah, thanks for catching that. Okay, good. Any other questions? Okay. The other thing, I'll just make a point. Again, I mentioned how the velocity is incorrect in this approximation. The other thing I want to say is that this prefactor to this term here represents the spatial decay, the spatial attenuation. Actually, the square root of that gives you the exponential decay. And in the case when mu sub s, when scattering is gone, mu tr is mu sub a plus mu sub s prime. So mu sub s prime is 0. Becomes 3 times mu sub a squared. And people who are familiar, the decay, spatial decay would be the square root of 3 mu sub a squared, or 1.7 times mu a. And that's also an incorrect decay, because we know from Beer's law that in the case of absorption only, without scattering, the decay should be just mu sub a. Okay. So you see the breakdown of the diffusion approximation both in space for high absorption and in time universally as far as time of arrival. Okay? So those are important. So I won't go through the details, but 2 very important cases in biomedical optics is the solution to the standard diffusion equation for a point source in an infinite medium, and for an infinitely large planar beam incident onto a semi-infinite medium. And you're going to get a chance over the course of the next 3 days to explore the characteristics of these equations. They're going to be reiterated to you, I'm sure, in following lectures. So I won't spend much more time on these. Only to emphasize again what I just said is that you have a spatial decay according to this mu effective, which is the square root of that 3a times mu a times mu tr. Mu tr is the sum of mu a plus mu sub s prime, and that this velocity, according to the optical diffusivity, is off. Okay, and so you'll get to explore these the behavior of these. So one thing I want to introduce, which I wish were more pervasive in the diffuse optics literature, because I think it provides tremendous improvement, tremendous gain, is something called the delta P1 approximation. This was developed many years ago, I think in the 70s and 80s, to improve significantly the diffusion equation for media which strongly forward scatter light. Okay, so and we saw many tissues, the typical single scattering anisotropy is 0.8, 0.9, 0.95. And as a result, if you describe the radiance and the phase function by this simple isotropic term plus cosine theta term, you're not going to do a very good job dealing with fields that are highly collimated, highly forward directed. So what we do is that we add one additional term in the radiance and phase function approximation. What we do is that in the radiance, we say the radiance consists of 2 terms, a diffuse radiance, and this diffuse radiance is exactly the same radiance we saw before in the diffusion approximation. It's just the isotropic fluence term plus an anisotropic flux term. But we also have a portion of the radiance which is collimated, which is directional along a single direction, which we call omega naught. Okay? And in the phase function, we say, okay, upon scattering, we're going to separate the light again into a diffuse component plus a collimated component, meaning a component that continues to propagate directly forward. So we say, let's take a fraction of the light upon scattering and let it propagate directly forward. And this is the second term here. This is a delta function. A delta function takes on a unit impulse when the argument of the delta function is 0. So when the direction times the collimated direction, the dot product between these two vectors is 1, delta becomes, you take a delta of 0, and then you basically get 2f. So you get some amount of light scattered directly forward, and then the remaining amount of light gets scattered according to the Eddington phase function. But since you have taken away some of the light and allowed it to propagate directly forward, the anisotropy value is modified. And moreover, you have now 2 degrees of freedom here. You have a degree of freedom of how anisotropic you want to make, or you should make, this single scattering anisotropy term, and how much light you're going to allow to propagate directly forward versus how much light you are going to diffusely scatter. And what that allows you to do is that it allows you to approximate the phase function with better fidelity. So if you just take these 2 general expressions for the radiance and for the phase function and put it into the radiative transport equation, you get a slightly different equation. Let's see if that works. There we go. And so here now we have a radiative transport equation with the delta P1 phase function. This is an equation for just the diffuse component of the radiance. So once you solve this, you would have to add on the collimated radiance. And it's the exact same equation, except the mu t term gets modified and the mu s term gets modified. And we call those mu t star and mu s star. And they're modified by the second moment of the phase function. So now we have an additional degree of freedom. We're able to match the angular description of both the radiance and the phase function, not simply taking into account the first moment of the phase function, but also the second moment. So we preserve, or we're able to capture, additional angular information of the light field. So mu s star here is mu s times 1 minus not g, but 1 minus f, this fraction of light that we allow to scatter directly forward. Or sometimes this is expressed as mu s times 1 minus g2. g2 is the second moment of the phase function. Mu t star is a modified transport coefficient. Instead of mu a plus mu s prime, you get mu a plus mu s star. And g star is a modified single scattering asymmetry or anisotropy term. It's related to the first moment through this. And then this Pe star is a modified Eddington phase function, and Q star is your diffuse source, or the scattered source. Not this actually we've taken away the collimated source. So if you solve this equation and add on the collimated source, then you'll recover the full radiance. Okay? Any questions about this? So the key thing is just adding this delta function here. We've done it to both the radiance and the phase function representation, and that allows you actually to, you will see, model collimated sources a lot better and improve overall our description of light fields that have a strong bias in one direction. Okay? Any questions? Okay. Okay. So we do the same thing. We put this into this radiative transport equation. We get what we call the delta P1 approximation to the RTE. So the equation looks exactly the same as the standard diffusion approximation. That's why there's very little additional mathematics to do. The only thing is that the source is just slightly modified. Instead of having mu s prime here, which is mu s times 1 minus g, the first moment, you actually have mu s prime times 1 minus the second moment, or 1 minus f. So what that allows you to do, so you have a term here, mu tr is mu a plus mu s prime, so you have the first moment in this term, the first moment of the phase function in this term. Here you have the second moment of the phase function. So the delta P1 approximation results are sensitive to the first 2 moments of the phase function and gives you a better angular description of your light field. And this is going to translate to what we shall see, tremendously improved distributions. This ends up just being a description of the diffuse light field, and again, we'll have to add on the collimated light. And we'll see that because in cases of high absorption, the diffuse light field goes away because there's no scattered light, and you can actually recover Beer's law using delta P1 in cases of high absorption. So this will improve the range of optical properties you can apply this approximation. Okay, so now we're going to move on to boundary conditions because, as you know, when you solve these partial differential equations, you have a second order spatial derivative here. So we need two boundary conditions in space. And today we're not going to talk about time varying problems, but depending on whether you're going to do the P1 or the SDA, you're going to need one or two initial conditions to deal with the time varying aspects. So let's talk about the boundary conditions here. So typically we're dealing with situations where we have tissue and we have some media of different refractive index on the boundary of the tissue. And so if you imagine this to be a greatly magnified view, and this green point is just below the surface, you have some angular distribution of your light field propagating upwards and trying to escape. If you're moving from a high refractive index medium to a low refractive index medium, you're going to get refraction, and the light will be bent away from the normal. But this only occurs so far, and you always have a fraction of light that escapes and a fraction of light that gets internally reflected, up to a certain point where actually Snell's law predicts that the refracted angle is 90 degrees or greater, in which case all of the light gets totally internally reflected. Okay? So Snell's law provides this relationship between the angles of incidence and angle of refraction of light crossing this interface. We know this from high school physics. And that there's a critical angle in the case of 1.4 relative refractive index to your environment and air-tissue interface for photons traveling at angles larger than roughly 45 degrees. All of that light gets totally internally reflected. None of it gets transmitted. Okay, so this is fairly basic. So the question is, how do we deal with this mathematically? So there is this well-known Fresnel reflection relationship that tells you how much light actually escapes. And so this plot here plots three curves. It plots the amount of light that gets transmitted across this interface as a function of your angle of incidence, how much gets internally reflected as a function of your angle of incidence, and then it gives you the angle at which the transmitted light is actually transmitted. And then above the critical angle, you get nothing transmitted, and of course, this angle of transmission is 90 degrees because it's just frustrated along the surface. So this is also a fairly well-known result from optics. Okay? So the question is that how do we handle this mathematically? Now, I'll just tell you a little bit about how it's done rigorously in Monte Carlo. There's various options. So the first thing I want to emphasize is that Monte Carlo handles the directional transport of photons rigorously on a case-by-case basis. So for every photon that approaches this interface, the subsequent trajectory of that photon is handled faithfully to the Fresnel relationships. The way you do this, there are multiple possibilities, and I'm just going to mention two of them. One way is actually to split the photon, to say, okay, we know from the Fresnel relationships that a portion of the photon gets transmitted and another portion of the photon gets internally reflected. So what we do is that we say, okay, we know what the Fresnel reflectance is. Let's let a fraction of the photon internally reflect and continue its biography in the medium, and let the remaining fraction escape, and if there's a detector in this area, we'll tally that weight as reflectance. Another option is only allowing either the photon to internally reflect or to transmit, depending on what the value of the Fresnel reflectance is. So you throw a dice, a random number between 0 and 1. If that number ends up being between 0 and the actual Fresnel reflectance, we totally internally reflect the entire photon. If that random number is between the Fresnel reflectance and 1, we let the entire photon transmit. So after accumulating sufficient number of photons that impinge on that boundary, you'll approach the same solution, okay, using either of these approaches. Okay, and that's called, it's kind of a roulette. The fate of the photon, whether it stays within the medium or escapes, depends on the value of that random number. Okay? Any questions about this? But the key point here is that we do a detailed balance at every point of the angular distribution of the photon, or the angular trajectory of the photon in Monte Carlo. We're unable to do this in the analytic approach. So what we can do is really deal with hemispherical integrals. And so what we say is this, is that the light that is coming downwards in this interface, from this interface, must have been light that initially traveled up towards this interface and got internally reflected. And that's what this equation says. It says, let me take the radiance at z equals 0, just below this interface. This should be 0 plus, actually. Sorry about that. Pointing downwards. So this is z dot omega. Z is the inward pointing normal. Omega is the direction of light propagation. So this is greater than 0 for all photon directions coming downwards. Okay? That light, the only place that light can come from at z equals 0 is that there must have been light that was traveling upwards. So this is z dot omega less than 0. Okay, that's going upwards. That got reflected due to Fresnel reflectance. And we have to integrate that over all angles. So this amount of light, the light coming down, has to be light that was formerly traveling up, but then got reflected at that interface. Okay? Then what we do is that we have this expression for the radiance, right? It's this isotropic term plus this cosine term. We put that into this, and you get this analytic expression, which is the fluence times some gradient of that fluence. R2 and R1 are the first and second moments of the Fresnel reflectance equation, which is this. So you can take the first and second moments of this Fresnel reflectance equation. You basically get values, constants, based on the refractive index mismatch, and essentially that equals 0. So this is known in kind of partial differential equations as a mixed or Robin condition. I'll also note here that this is equal to 0 in cases where there's no sources at the location of the boundary. Now, if you had a collimated source in the same area, you're going to have a source term here because the source also injects light going in, right? So the light coming down is not only the light that went up and got reflected back down, but also any light that is injected downwards into the tissue. So in other cases, you'll see a source term on this right-hand side. Okay? Okay. Any questions about this? So the key issue here, again, we have to introduce an additional approximation. Even the boundary condition is approximate here. It's not handled on a detailed angle-by-angle basis. You actually have to integrate over a large interval of angles in order to handle that. Okay. So the refractive index mismatch is challenging because it actually introduces discontinuities in both the magnitude and the angular distribution of the radiance across the boundary. And really, accurate computation of reflectance must properly account for these effects. And here is an expression for how you would tally the reflectance. And this is mapping the radiance going upwards in the tissue versus the radiance that exists on the other side of that boundary. Okay, so that's the theory. So now we're going to start showing some results, okay, to try to build your intuition. So the heavy mathematics is done for today's lecture, and you know, if people are so driven to pursue the mathematics further, I'll definitely provide plenty of resources. But part of this is also to start to build intuition, okay. So what I want to try and emphasize here is that we have several sources that one typically uses, both in therapy and diagnostics. We talked about kind of the laser source, which we sometimes term as a pencil beam. In therapy, we often use spatially extended sources laterally, with have some sort of Gaussian beam intensity distribution with a differing radius. And then a very useful case to understand the physics of the light transport is just to consider the one-dimensional case with a beam of infinite lateral extent impinging on a semi-infinite or a slab. There are really, from my point of view, three important metrics that one can use to visualize and understand these distributions. One is the fluence rate as a function of depth. So I'm going to be considering in this, the rest of this talk, semi-infinite media, something that has infinite extent in Z that's homogeneous. So this is good to understand the detailed fluence rate profiles. But if you want to understand the trends in this fluence rate across a range of optical properties, I don't want to be showing sets of fluence rates for changes in optical properties. I want to define some scalar metrics that I can then plot as a function of optical properties. And as we discussed yesterday, how much the light penetrates is of critical importance. And you can imagine two different ways of defining a penetration depth. One is to say, okay, I have an incident field of some unit intensity, and I want to know at what depth does that intensity fall to 1 over E of that incident intensity. I'm going to end up normalizing these metrics. I'm going to call that pi, Greek letter P, penetration depth. Okay. Another way you can imagine to express penetration depth is, especially for a therapeutic application, you're often interested in where is most of the energy absorbed, right? So the fluence rate, if you take the fluence rate and multiply it by the local absorption, that is the actual temperature rise or absorbed energy dose. So you can integrate this distribution, and I want to see where does roughly 2/3 of the light get absorbed. And that's what's relevant for therapy. And I'll call that a dose depth or capital delta. Okay, so you're going to be seeing some plots of pi and delta as a function of optical properties, which I think will help you. And we're going to show results from Monte Carlo as well as standard diffusion and delta P1. Okay, so these penetration and dose depths provide useful metrics to evaluate the spatial extent of the fluence distributions. Okay, so let's get started. One thing I want to emphasize again is that in the standard diffusion equation, you have a natural spatial decay rate for the fluence rate. It goes as this mu effective term. Mu effective again is, or mu effective squared is 3 times mu A times mu TR. This is the source configuration. And this decay of the source term is usually expressed in terms of mu TR, which is this sum of the absorption and the reduced scattering coefficient. So this is what happens in the standard diffusion approximation. But in the delta P1, you have the same spatial decay of the diffuse light, you have a slightly modified source term, and the decay of the source occurs according to mu t star. It's sensitive to the second moment, not the first moment. And that will make a dramatic impact on the predictions. Okay, so what I've first shown here is Monte Carlo simulation results of the fluence rate as a function of depth. I've normalized the depth in terms of the transport mean free path. So we talked about the transport mean free path. It is the length in tissue that on average a photon has undergone either an isotropic scattering event or an absorption event. Okay, so it's 1 over the sum of mu a plus mu s prime. And what I've done is that I've plotted results for differing ratios of the reduced scattering to absorption. So when it's very high, we have a dominant scattering situation. So diffusion should probably work fairly well because there's a lot of multiple scattering. And then cases where there's higher absorption. Here I've plotted results where there's no refractive index mismatch at the boundary. Okay? So you see a few things. You see that the attenuation increases as absorption becomes more dominant over scattering, which kind of makes sense. You're going to be losing photons. You see actually you have higher fluence rates at the surface when you have high scattering because you got scattering coming back. And you also have a peak in the fluence for high scattering that it's not at the surface but a little underneath the surface. Does anybody have an intuition for why that might be the case? Yes, Michael.
It's losing its collimation, though.
Well, you're losing collimation throughout. It's because light here at the surface is escaping. So you're getting a local depletion, right? So, and so it's actually the spatial gradient, which actually is due to the leakage of light. And as you get less and less scattering, there's less leakage of light, and this subsurface peak goes away. Okay. So your reflectance actually, which I won't show here, actually goes down as your absorption increases. Okay. So the first thing I want to do is to think about what if now we put in a refractive index mismatch. If we now say, okay, instead of having a tissue, say tissue-water interface, which is almost perfectly index matched, we then look at a tissue-air interface. How do you imagine these fluence rate profiles would change? Would anybody venture a guess? Would anybody like to venture a guess? What happens differently in this system when you have a refractive index mismatch here?
Total internal reflection at the boundary.
That's right. So in this case, every photon that approaches that z equals 0 boundary will escape. And now once we put a refractive index mismatch, a subset of those photons are going to get reflected back in. So what do you imagine? Do you think then the fluence rate close to the surface, will it be higher or lower? Higher. Precisely. And do you think all of these will go up by the same amount universally? Or will the impact be biased towards a certain set of optical properties?
Bias towards more highly scattering. There's more opportunities to reflect back into the tissue.
That's right. So it's going to be biased to more high scattering tissue. And that's what we see here. So now the open circles are the Monte Carlo results for a refractive index. And you see that there's a bigger difference for the high scattering case, and there's very little difference in the low scattering case. You see a slight increase here. Okay. Now let's see how the standard diffusion approximation does. So this is what the standard diffusion approximation predicts. You see that in high scattering conditions, it's fairly good down to depths of about 2 transport mean free paths. And then you get a severe or an important under prediction in the fluence rate values. I want to emphasize this fluence rate is being plotted in a logarithmic scale. So even small differences are fairly significant here. But deep, you see fairly good. Now, as absorption increases, you see that the errors close to the boundary are magnified. They get worse. And that's, again, because the light field is very anisotropic. And you also see, actually, the decay rate in the far field at large depths is also poor. And that's because this mu effective term is not the right rate of spatial decay. Okay? But we see that if you're at larger depths of around 2 transformation paths, you have strong scattering. Standard diffusion does fairly well. Delta P1 predictions, which are here, do remarkably well. And that's because in the cases for high absorption, you have a better representation of the collimation of light, and you have a better representation for the decay of collimated light. And so, and again, the mathematical complexity is no higher than SDA. And in fact, in this case, the fluence rate predictions are within a relative error of 10% across the entire range of optical properties. Okay, so now I want to show these penetration depths, or these dose depths. So this is a fairly involved slide. So what I've done here is I've plotted dose depth in dimensionless units. So I've taken the optical depth, the actual physical depth that the light penetrates, and multiplied it by mu effective. Mu effective is that rate of spatial decay of light fields predicted by the standard diffusion approximation. Okay? So this is dimensionless because mu effective has units of inverse length. Okay? The symbols are all Monte Carlo results. I've plotted 2 depths. The penetration depth, pi, which is the depth at which the fluence rate falls to 1 over E of the incident light. And this dose depth, which is the depth at which, when you integrate the energy absorbed, you get roughly 2/3 of that energy absorbed. Okay, so you see the impact of refractive index. Refractive index, as you saw earlier, when you increase the refractive index mismatch, you get a deeper penetration of the fluence rate. You know, fluence rate is higher throughout, and you see that here. So for the larger refractive index, for high scattering, you have a much higher penetration when you have refractive index mismatch compared to no refractive index mismatch. But that difference goes away as absorption gets larger, okay? Because the total internal reflection is much less of an issue. Interestingly, the depth in which most of the light is absorbed is not impacted by the refractive index mismatch so much. Because what happens is that even though you have higher fluence rates, you're also depositing different amounts of energy in the tissue when you have a refractive index or not. And when you integrate, basically it all washes out. So that's important to know. The other thing is that, just one thing that's important to know is that for cases of high absorption, all of these values converge to a value of around 1.7. And that's, again, because mu effective, let me just write mu effective down. Again, this is equal to the square root. Okay, that's the value of mu effective. So in the case of high absorption, mu s prime goes to 0. Mu effective is the square root of 3 times mu sub a. And if you multiply the actual depth will be 1 over mu sub a. So basically what you're left with is a square root of 3. And so that's basically a square root of 3. Okay? So that just tells you that you recover Beer's law in cases of high absorption, which you should. Okay? So now let's look at how standard diffusion does for predicting these things. So the good news is that standard diffusion actually does fairly well in understanding the depth of penetration of light doses on a local perspective. So if you look at ratios of scattering to absorption of, say, anywhere from 10 or so, 10 to 100, it starts to be good. But below about, depending on how much you're willing to how much error you're willing to tolerate, for mu-s primes or mu-a's less than about 10 or 100, it's really catastrophically bad. The dose depths are pretty much universally bad unless you get out to ratios of scattering of absorption of about 100, but it's actually really, really poor. Delta P1 does remarkably good. Okay, and so again, that better handling of collimation really does a lot of good. One thing I do want to point out, if there is an area where delta P1 is poor, it's an area where mu-s prime and mu-a are about the same. So you start to see some errors in here, but it recovers nicely in limits of high absorption and does very well in limits of high scattering. Okay, but delta P1, you're going to see some problems with it between 0 and 10. I'm sorry, 1 and 10 of ratios of mu-s prime or mu-a. Okay. Any questions about that? Yes, Vikrant. Hold on 1 second. Let's just bring the microphone. Yes, Vikrant.
So the delta P1 approximation does not have that constraint of mu-s or mu-s prime being much greater than mu-a?
That's right, because it does two things. Number one, it separates the radiance into a collimated term and a diffuse term. And so actually, in the limit of mu-a getting large, the diffuse term actually goes to 0, and it retains the collimated term. Standard diffusion has no mechanism to handle collimated light. And yet, in the case of high scattering, delta P1 essentially becomes the standard diffusion approximation. But even actually close to the source, it's better too, because it handles the collimation close to the source better. It starts to have difficulty when scattering and absorption are comparable, because it's not perfect still. It's still having a collimated term to deal with the forward direction, forward directed propagated light, and still has this constant plus a cosine theta term to deal with the diffuse light. And here, the diffuse light, it has a more complicated variation than just an isotropic term plus a cosine theta term. There's other stuff going on that delta P1 can't accommodate.
So is that true also for if you use a diffuse source with a small separation, for example? Can you use delta P1 approximation there and expect good results?
So what do you mean by diffuse source?
Diffuse source in the sense that it's not a collimated beam. It's, let's say, a diverging beam that you're trying to use typically in diffusion regime, or like when you use diffusion approximation, you try to keep a constraint on source detector separation to be greater than a certain number,
yes,
typically 5 millimeters or
sure,
more. And if you had P1 approximation or delta P1 approximation, could you come over that constraint and just use a smaller separation?
Sure. Delta P1 definitely allows you to model smaller source detector separations better. But I think at least the first part of your question had to deal with diffuse sources as opposed to collimated
Right,
sources. And that's a more subtle point. Because again, mathematically, the source is treated as moving in one and only one direction. It doesn't have the ability to handle a finite aperture, at least not identically. But I imagine one can explore various options to doing that. You can still, in the delta P1 on some level, deal with planar sources at least that approach the boundary at an angle. But if you have something that is of finite lateral extent, but also have a finite aperture, then delta P1 can't model that situation exactly. At least it cannot represent that source exactly. But there are other approaches that we've taken dealing with more expanded spherical harmonic techniques that do. And actually the person who does that actually is not here for the rest of the week, but we can talk about that. Okay. So we have other techniques to handle that. Jerry, do you have a comment about dealing with more complicated sources? No.
No, I think you covered it.
Okay.
Pretty well.
Okay. Other questions? Okay. Good. So now let's look at finite beams. Okay, the previous results were for these idealized beams of infinite lateral extent, but in reality you have finite beams of finite size, and how does that compromise your penetration? So here I'm looking at Gaussian beams with radii of different radii. Here is radii of 100 transport mean free paths. So a beam that's literally 1/10 of a meter in radius. And so it's actually fairly similar to the 1D case. As you shrink that beam, so this is like a 1 millimeter beam, this is a 3 millimeter beam, 10 millimeter beam, you see significant drops in the in the fluence rate, both the magnitude and the attenuation. And this is the fluence rate along the center line. It's along the center of the beam. Okay? So what happens here is that as the beam gets smaller and smaller, you see that the scattering allows the light to basically escape to the side. You get lateral dispersion and you get depletion of the light more rapidly along the center line. And I didn't show the standard diffusion approximation predictions, but the delta P1 predictions do fairly well, except when the beam starts to get small. So when the beam starts to be on the order of 3 transport mean free paths, you start to see some errors at proximal depths, but at larger depths it still does fairly well. If you look at a case where you have much stronger absorption, say mu s prime or mu a of 1, you see that there's not as much drop in the penetration with reductions in beam diameter. And that's because there's just not a lot of scattering. Okay? Photons are more likely just to go straight and get absorbed rather than to undergo scattering. So there's not a lot of lateral dispersion due to scattering, or not as much at least. You see that the first data point I plotted was at 30. That's because 30 was essentially substantially equivalent to the beam of infinite lateral extent. And the spacing is much tighter. You start to see delta P1 break down. It doesn't get give a very good description of the decay rate because it's in this regime where absorption and scattering are comparable, and the light field is fairly complicated to handle from an analytic perspective. But then again, Monte Carlo would provide a much better prediction. We can also look at optical penetration depth of these, and you can see the loss of optical penetration depth for high scattering as you go to smaller beams. Delta P1 does very well in predicting that, and also this dose depth. You can see delta P1 does a little worse job, especially at small beam diameters. And we have some more details about that, about the characteristics of these curves, which you can read at your leisure. And then these are just some graphical depictions of the light fields. The color is Monte Carlo. The solid contour lines is Monte Carlo, and the dotted dashed lines are the delta P1 approximation. And so you can see that there's actually fairly good agreement between the contours between these two approximations. This is a strongly scattering case for a beam roughly 3 millimeters in radius, and this is a strongly absorbing case. One thing I want to emphasize is that the lateral extent of these Gaussian beams for high scattering media is dominated by the rate of scattering, whereas the lateral extent of these beams in the case of strong absorption is basically determined by the size of the beam, because there's just not a lot of lateral dispersion. Okay? And so to finish up, I just have really one more case I want to talk about a little. In this case is really important for diagnostics as well as for extracting optical properties from ex vivo tissues. And this is a case where you have a beam of infinite lateral extent on a turbid slab with optical properties mu a mu s, some single scattering anisotropy G, and some slab thickness, which I'll call lowercase d. Okay? And so our analysis, which I haven't been able to run Monte Carlo simulations on yet, but I've solved this problem in the delta P1 approximation, and Rolf will show us some results later, I think, or at least illustrate cases where a rigorous RTE solver was applied to this situation. We'll look at both the internal fluence rate distribution and as well as the reflectance and transmittance, because in this case, not only do you have reflectance out the front surface, but you also have transmission on the other side. And actually having access to measurements of both of these can tell you something about the optical thickness of this slab and the absorption and scattering properties. Okay. So first, I just want to visualize some of these distributions. So these are results from the delta P1 approximation. So they're not exact. They may not be perfect, but hopefully they're I imagine for large slab thicknesses, they should be pretty good. So one thing I just want to emphasize here is that this graph is a little confusing. So here, the x-axis is a normalized distance into the slab divided by its thickness. So, and I'm showing slabs of different thickness. So, so obviously, the black slab is 1/12 the thickness of the red result. Okay. So you see, for the thickest slab, you have, again, just like the results in a semi-infinite media, you have this subsurface rise. I put it on a linear plot this time, and a decay. As the slab gets thicker, as the slab gets thinner, you get a little drop, and then, of course, actually the fluence rate at the backside starts to increase because the slab is thinner, right? So as the slab thickness goes down, the reflectance goes down because there's less material to backscatter the light back towards the front, but you get more light leakage out the back. Okay? So, and this is for a highly scattering medium with a refractive index mismatch. So you have air on both sides, okay, and the tissue in between. So for large scattering, increases in slab thickness increases the fluence rate close to the front surface. It actually increases the reflectance, as you'll see, but it decreases this is incorrect. It decreases the fluence rate. Oh, no, this is correct. Increases in slab thickness, increases the fluence rate near the front, but decreases them during the back. Sorry. Okay. Things change a little bit if you have refractive index matched boundaries, right? The fluence rates drop pretty much uniformly. Okay. For high absorption, things are a little different. So here's scattering dominating absorption by only about a factor of 5. The reflectance or the fluence rate close to the surface is really insensitive to the slab thickness. And that's because there's not a lot of backscattering. Okay? And you have a lot more attenuation as your slab thickness gets larger. So changes in slab thickness don't really affect the fluence rate at the front surface, but you have a big drop with increased slab thickness at the backside. And this gives rise, and then you have a less of a dramatic change when you have a refractive index matched system. And things change a fair bit with reflectance and transmittance. So here is now plotting reflectance as a function of slab thickness, as a function of optical properties. So you see that you're not going to get a lot of reflectance for highly absorbing slabs, and actually you're very insensitive to slab thickness from a reflectance measurement, even for tissues where your ratio of scattering to absorption is 10, which is a fairly reasonably scattering tissue. It's only beyond that do you actually start to see sensitivity in your reflectance to the slab thickness. Okay? And you see changes with refractive index mismatch. And then you can also plot either transmittance or absorbance. And I chose to plot absorbance because transmittance has a similar feature than reflectance. And so the plots really overlay. So if you think about the amount of light that's lost, for strongly absorbing tissue, of course, you're going to lose almost all the light due to absorption. You have very little reflectance and very little transmittance. But as your scattering goes higher and higher and higher, you're going to reduce the amount of absorbance. And that absorbance is going to be smaller for small slab thicknesses than for larger slab thicknesses. And then if you sum these two and subtract that sum from 1, you'll get the transmittance, because the absorbance plus the transmittance plus the reflectance should be 1. Okay? And the black lines here I've shown is for a slab of infinite extent. So there'll be no transmittance, but you'll still have absorbance. So, yes?
So in a highly scattering media, which is going more towards the right, if I understand correctly.
Yes. Strongly
So-
scattering medium, yeah.
Yeah, strongly scattering medium, your beam, as we saw from the simulations yesterday as well, it's pretty much going to be, at the surface. So if your slab thickness at certain point should not matter after that, right? If you're having that much reflectance back because of scattering, and your distribution of your beam in the tissue is pretty much a bulb around the surface source. So if that's the case, do you expect that after certain thickness you're not going to see that effect?
You're not going to see which effect. Let me just...
The thickness of the slab is not going to matter for reflectance.
Well, you continue to see, so this is the difference between these last two curves is a difference between a slab of 12 L star versus an infinite slab. So you will still see differences in reflectance. Remember, even though you have a lot of backscatter, you still have forward scattering. And if you have a high scattering medium, you're not going to be losing the light due to absorption. So light will continue to percolate through.
Right, but I mean, let's say like a ratio is one thing, but there's also absolute value of scattering and absorption. So if the absorption is high enough, light is not probably going to penetrate beyond a certain distance at all. So if, in that case, if the thickness was 12 and if absorption was high enough, although the ratio was still similar, then you may not see anything coming out on the other side.
Well, I mean, all of this is dimensionless, right? So this is in terms of L star, which also takes into account mu A.
Okay.
So that's the other thing you have to recognize, right? So these thicknesses are normalized relative to not only the scattering, but also the absorption.
Okay.
Okay?
I missed the L star.
Okay. So I just have a summary, and instead of recapitulating the teaching objectives, I wanted to provide more details. So I just want to emphasize that, number one, the standard diffusion and delta P1 approximations, use analytic representations for the angular distributions of the radiance and the phase functions. And they provide a really useful way to get closed form solutions or more rapid solutions. You can also implement numerical solvers for these approximations, which are useful for complex geometries. One thing that also occurs when you use these analytic representations is that you're unable to represent the boundary conditions rigorously. So one thing I want to emphasize is that Monte Carlo transport solvers handle boundary conditions and refractive index mismatches rigorously on a photon by photon basis in accordance with the Fresnel relations, whereas these analytic solvers handle these mismatches by enforcing energy conservation globally using hemispherical integrals. refractive index mismatch between tissue and boundaries generally enhance the total internal reflection and increase the fluence rate and optical penetration within the tissue. And they do that because they actually mitigate some of the reflectance coming out. So more energy is trapped inside, and therefore there's more light available within the tissue. The standard diffusion approximation provides, I would say, poor predictions for the internal fluence rate and optical depths for ratios of scattering, reduced scattering to absorption of 30 or less. Delta P1 provides dramatically improved predictions for these fluence rates and optical depths with almost no additional overhead in computation. But these predictions do tend to break down for small beam radii and for comparable values of mu A and mu S prime. And then finite beam diameters further reduce the optical penetration and dose depths, especially in highly scattering media, where scattering will provide effective lateral dispersion of the light. And we'll close at this point and be happy to take any additional questions. Samer.
Just a quick question on the last bullet point. I probably missed it in the slide
Yes.
somewhere.
Yes.
But for those varying beam diameters, is the total energy in the beam considered to be the same, or is it like a energy density that's considered to be the same? So how exactly is that?
So the definition was independent of magnitude of light being injected. So they were, remember, for the penetration depth, it was defined that if you have a unit of energy coming in, at what depth would the local fluence rate drop to 1 over E of the incident? And for the dose, at what depth does 1 minus 1 over E of the total amount of energy get absorbed? So everything is done in dimensionless terms. And that's one thing I should emphasize, is that the radiative transport equation and these diffusion approximations, they're linear, right? So there's no nonlinearity in these processes. So you can scale them. Okay?
Thank you.
Yeah. Question? Sylvain.
Just a quick question, just regarding the virtual tissue simulator.
Yes.
I was playing with it. I noticed that on the forward solver, you didn't implement delta P1. Correct?
No.
You did in inverse and not influence, but in spectral panel as well.
Yes.
I guess. But you didn't do it in. Is there a reason, or are you guys going to develop launch that? Or?
Yeah, we'll get there. They haven't been implemented yet. The one challenge or limitation is that you notice that in our forward solver, we implement the solvers for all solution domains. We provide solutions for as a function of space, spatial frequency, time, and temporal frequency domain. And so we haven't quite done all those variants of cases for the delta P1. And so we rather give it all or none at all. But I'm happy to work with anybody who wants to implement delta P1. I think for many, many cases, it's definitely worth doing. And so if anybody has interest, just let me know. I'm happy to help you. But thanks, good question. And now some motivation. Good. Any other questions? I know there's a lot of information in this lecture, and kind of probably maybe take a coffee break and then let you guys relax a little and then maybe open up for questions more just before the next lecture. So thank you guys. So now that we've had some caffeine and sugar, maybe we'll have some questions at all? Okay. Gage.
So this was probably touched on in the first few lectures of the first day a little bit, but I'm still having a little bit of trouble kind of understanding. The Monte Carlo simulations are kind of considered a gold standard to model photon transport. So in what cases would you really want to use the delta P1 approximation to model photon transport, and in what cases would you want to just stick with using Monte Carlo methods?
Well, that's a multifaceted question. So any analytic formalism has challenges when you have complex geometries, certainly. So if you have a complex heterogeneous tissue system, you're going to have to work a little harder to get solutions in an analytic formalism. Now, certainly, these analytic systems can be dealt with numerically within some sort of finite difference scheme, certainly. There are always conditions where these analytic formalisms break down, even though the delta P1 does do a lot better than the standard diffusion approximation. It still has difficulty in certain ranges of optical properties and for narrow beams and narrow dimensions. Whenever you start to approach length scales on the order of a single transport mean free path, you start to see breakdowns that can only be improved upon by taking higher order moments in the Legendre polynomials or spherical harmonics. And, but there are other approaches to take for those if you want to keep analytics. Monte Carlo is much more powerful. It gives you much more detailed information, and it's easier to deal with complicated boundaries and heterogeneous media. And our group and others have made important advances in using Monte Carlo not just to deal with forward problems, but with inverse problems. And with developing improved estimators that allow you to achieve simulations with high figure of merit in very small real time. But it's really problem dependent and depending on what your objective is. So I don't know if there's any real simple, easy answer to that question. So it's really situation dependent. Jerry, do you have any? I'm sure you have some comments to make.
I think it's fair to say that the answer to the question is a function of time. And when we are able to push the envelope further with Monte Carlo, I think you'll want to use it more frequently. However, it's a fact that standard diffusion and delta P1 are in wide use and are very useful in a whole lot of situations where the approximations are relatively okay to use. And that's because they're so fast. So, if you need to do something with clinical real-time work, then you'll be using these kinds of methods until we get a Monte Carlo tool that can support real-time information delivery.
But to amplify on that, though, there are well-defined ranges where delta P1 and SDA break down. And one thing that people have done who don't want to sacrifice the fidelity of a transport rigorous computation is to do the Monte Carlo simulations up front, save them, and use lookup tables to recover properties. And we do that at the Laser Institute quite a bit. I know we have a student from Nimi Ramanujan's group who uses Monte Carlo and scaled Monte Carlo techniques both in a forward and inverse way. Now, doing scaled Monte Carlo for inversion is powerful, but also you do incur errors, and there are some limitations to that, so you have to do it carefully, but you would also have to use standard diffusion and delta P1 carefully. But there are ways that you can pay that Monte Carlo cost up front and then save it and either access it or post-process it, in the case of, say, perturbation and differential Monte Carlo as well, to do inverse problems. So,
yeah, I think if I can speak for the VTS group, which is so talented, I think what we'd like to be able to say we have is a pretty fast Monte Carlo solver if it's approximate. Right now, scaled Monte Carlo would be our candidate for that, I guess. But we'll gradually improve the true Monte Carlo, the gold standard Monte Carlo, and make it better and better. And so but we'll always have something and various tools that you can use for a whole variety of situations.
One other thing I just want to emphasize is that much of the week you'll be using this graphical user interface, this GUI, but the GUI is just a projection of, I would say, a very small fraction of the entire code base. And of course, you've already used the command line and the MATLAB interoperability. But there are many, many features of the Monte Carlo simulations, as well as the analytic solvers that we have within the code base that can only be accessed through the command line. So, one thing that we're using the workshop to do is to provide just a general platform of understanding and knowledge. And of course, presumably all of you are here not only to learn, but also to hope that this workshop can advance your own research. And if you have particular considerations, particular problems that you don't see directly addressed by the online tools, come speak with us, and maybe we have tools that provide a better match to the sorts of problems you're seeking to solve. There was another question, I think, other than Gage. Yeah, Matt.
So can we go back and talk about the sources a little more? I know in the standard diffusion approximation, you usually use a laser in real life, right? But the standard diffusion approximation can't have a collimated source, so you replace the source with a diffusive source under the surface, right? Does the delta P1 approximation mean you don't need to do that?
Okay, so there are a couple different ways that the standard diffusion approximation deals with collimated sources. The first way it was done was you just replaced the entire collimated source by a single point source that was embedded a certain distance, typically L star below the surface. Or you can actually do a line of point sources that are exponentially attenuated with distance. And that's actually the implementation I used to generate the results that I showed. That source configuration has been shown to provide better results within the context of the standard diffusion approximation. In delta P1, you also, in some sense, so there's, if you remember the phase function, there was a fraction of the light that was directly forward scattered that remains collimated, and then there was the remaining fraction that was allowed to scatter diffusely according to a modified Eddington phase function. So that source configuration that you use, that decays differently than the standard diffusion equation because it's dependent on the fraction that you scatter forward relative to not scatter forward. But it still is effectively an exponential decay of diffuse sources that are used in the delta P1, which predicts the diffuse light field. And then that prediction, after you get that from the delta P1, you have to add the collimated field back on to get the predictions I showed. And that's just adding another exponential. Hopefully that addresses your question. Okay. Yeah. So there are always subtleties which I don't go through in the lecture, but they're not difficult.